Hello everyone. Let's talk about capacitance today. Okay. So a simple capacitor is two parallel plates. And this is actually the schematic symbol that we're going to see on circuit diagrams. It looks just like that. What a capacitor is, if we think about they're conducting plates, and if we apply a voltage across it, what it's going to do is going to separate the charges into positives and negatives. So if I were to attach this thing to a battery, so I'm going to draw a simple schematic circuit diagram here. So if you know what, I'll actually draw it so it looks like a battery. All right, so if I took two wires, attach them to two sides of a battery, positive, negative side of the battery, what's going to happen is the electric field that is being generated inside of the battery due to the chemical reactions is now going to extend throughout the wire and go to these parallel plates. Okay. So what's happening inside of the battery is there would be one material that is attached to that lead interacting with another material that is attached to that lead, and the chemical reaction is allowing the separation of the electrons from one of the chemicals. So then they're trying to attract towards each other. So if the green material ended up gaining more electrons from the red area, that would become positive. So now these positives are trying to attract to those negatives, but however the internal structure of the battery is, they can't just move through the chemicals. So if we attach a wire from one side of the battery to the other, what's going to happen is those charges are going to attract to each other. All right. So by attaching a wire and putting this wire attached to or very near another wire, what's going to happen is that electric field is going to be generated throughout that whole conductor, and then those positives and negatives are going to pull towards each other, right? So if originally these are both neutral, this positive charged object is going to have a field that radiates away. This one's going to have a field that radiates towards, and it's going to generate an electric field in between those plates in that same direction. So this plate on the left that's attached to the positive side of the battery becomes positive, and this side becomes negative. All right. And again, if you think about it, these negatives are trying to be attracted to those positives, and the more negatives that end up on this side are pulling more positives towards that side. And the word capacitance, I mean, should make sense with a capacity. Basically, how much charge can be put on these plates. So capacitance is a relationship between the amount of charge and the voltage that is applied across the plates. So depending on the voltage of this battery, if it's a 9-volt battery or a 1.5-volt AA battery, these numbers are going to affect how much total charge is ending up on the plates. And the proportionality constant is what's called capacitance, C. So our equation is Q is equal to C times V. Now, the capacitance doesn't depend on the charge and voltage. The charge depends on the voltage and what the capacitance is. So like this is a constant. So if I have a 1 farad capacitor, that's going to be the unit for capacitance, all right, that will always be 1. So if I change, if I put a 1.5 volt battery here, I get a charge of 1.5 coulombs. If I put a 9 volt battery here, I get a charge of 9 coulombs, all right, because that capacitor is not changing. So if I have 2 plates, again, supplied with some voltage there, what's going to happen is, well, let me put the battery. Now this is a schematic symbol for a battery. It's going to be a long side and a short side, where the long side is the positive. So that means that this plate is going to get filled up with positive charges all along its surface. And this one will, those positives will pull the negatives from the other side of the battery, and those will line up on that side. Now, the charge on each will be the same. So this will be positive Q, this will be negative Q, and they'll be equal. So those plates will fill up to their maximum capacity based upon whatever that voltage is. The amount of charge that can be held on those plates is simply based upon the geometry of those plates. So if I was able to stretch the plates out so that they were longer, I would now have more space for the charges to accumulate. So longer plates, and again, remember these are plates, so if I stretched out the plate, even if I didn't change the width, I have a larger surface area, right? So it is the area that is going to be the factor that allows more charge to be placed on them, and area is the factor that changes the capacitance. Now remember, this entire time there is a constant electric field strength between those two, right? Now what happens to that electric field if I was able to separate, pull the plates apart, right? So if I was able to take this plate and move it over here, what is going to happen to the strength of the electric field in between there? Now, if there was no battery attached, if there were none of this wire attached, you should have said probably that it's not going to change, because we've looked at parallel plates that are charged, and we know that the electric field is constant as we move through it. Now, since we move these away from each other and there is a source of the charge, what happens is the amount of attractive force between the positive charges and the negative charges will now decrease. So what's going to happen is there will be less positive charge that is going to accumulate on the left-hand plate. Well, that didn't work. And I can't erase it. All right. Which means there's going to be less negative on the other plate. And if you think about this just in electrostatics, if we had a source of charge and we moved those two things closer to each other, just like polarization in insulators, right? The closer it is, the stronger the pull, the more the charges will be pulled towards. The farther away, the weaker the pull. So that's what's going to happen in these plates if we keep moving them towards each other and away from each other. The force is going to be greater to be able to pull more charges to each plate the closer they are. If you move them away from each other, and of course if you move them infinitely far away from each other, there's going to be no pull at all. Okay, so the distance that separates this is also the factor that changes the constant capacitance value. All right. Still looking at our plates here. This is positive, that's negative. We have the net field going this way. If we were to use Gauss's law and encompass the entire length of the plate, so length L, And this is a plate, so it has some width here. And we apply Gauss's law. And if we solve for the charge that's going to be enclosed over the entire plate, all right, we would get the total charge. If that's a value of little q, we would have the charge is going to be equal to epsilon naught times the strength of the electric field, which is constant, and then the area of the plate. Now this is a special case for parallel plates, and with parallel plates we know that the electric field at any point in between is the same. So from the last chapter, the electric field is related to the electric potential by the equation V is equal to E times D. So by substituting in for E, we'll get that the amount of charge on a capacitor is equal to epsilon naught times A over D times V. So that part right there matches up with what the capacitance equation looks like. So we have that the capacitance depends on the constant, the surface area, and the distance of separation. You can see it's just the geometry of the parallel plates. This is only for parallel plates. This is for any shape. All right. So what's the difference here is that electric potential ends up being a different relationship, and of course it changes as a nonlinear function of distance. We're going to look at the more complicated situations like spherical capacitors and cylindrical capacitors in another video.